Hello, everyone. Thank you for joining this session. My name is Mehdi Bahrami, and I'm going to present how to build a foundation of AI-based healthcare system through language models. I'm a researcher at Fujitsu Research of America. We are located in Sunnyvale, California. I have been working on a variety of the projects during my PhD thesis around the cloud computing and a slightly shift into the NLP and producing different systems such as API learning. And currently, I'm working on language models. So I'm going to present how language models can help in healthcare systems. All right, so in this talk, I'm going to focus on why we need language model and what is the language models. And then we will focus on a variety of the different language models, and we will look at how those language models could help in healthcare system scenario. So we will look at the word to vector, graph, transformer, and BERT. All right, let's get it started. So first, why language model? So the question is, when we look at the health record system or EHR or electronic medical records, we see currently there is a trend that we need to capture the data, we need to process the content, and then we need to facilitate to remove the burden relating to the use of health, IT, and EHR. So what is actually language model? So what we can do with language modeling? So let's assume that we have a text. That text say we have adult age 14 to 75 years with a diagnosis of diabetes. Uh, with the goal is to understand what is the next word after appearance. So that's how language model try to learn. So if we process the different contexts, different text from variety of the large corpus, we could able to look at there is a fasting possibility, there is a LDL, and still we can keep continue this approach for the next word. So in terms of the selecting LDL, what would be the next level? Would be LDLC, and then what would be the next one? Would be level of 17, and we could complete this sentence by processing the large number of the text, and statistically we can understand what how likely one word could appear after another word. So that's a main target of the language modeling. So in addition, we could also look at, let's say we want to look at the answer the question, diagnosis of diabetes. So if you look at the 40 to 75 years, we might consider look at the different texts, and then we may end up a set of range of years that appear for diagnosis of diabetes without even collecting information from the patient. So by processing the large number of the context from the, for example, internet, Wikipedia, or sometimes from the EHR records, so we could generate these statistical analysis to understand what would be the results for the years period for this section. We also could say, for example, if we have an adult age between 40 to 75 years, what would be possibly diagnosis appearance? So, for example, in this case, we could find the diabetes. So that's how language model works. So in more detail, we're going to look at the context. For example, the multiple rows shows the different texts. And then we have diabetes, as you can see, type 1 diabetes that shows develop at any age, insulin resistance, as well as we can say in people who have particular HLA complex. So now basically we are looking to understand about the diabetes. And these diabetes words can be learned from the context. That, for instance, we can understand what would be the semantic similarity for the diabetes, or what could be possibly for these red color appearances. So all those statistical, basically we are looking to understand the probability of the word in terms of given context. So by processing this context, we might consider a window that generate how many words before and how many words afterward we could use to understand the context. So in this case, currently we have the k equal to 4, as we can see here. Then we will able to process the previous and the afterward words to understand diabetes. So there is a different approach to train the different models to understand this structure. So first of all, we're going to look at the word to vector. In the word to vector, there is a two scenario. One of the approach is continuous bag of the word. So in the continuous bag of the word, we basically look at different words that appear before diabetes and before and after the word, target word. So, and another approach is using the skipgram. So the skipgram going to select the diabetes and then look at the one word before, two word before, and one word after, and two word after. So in this case, currently we're considering the sliding window with size of 2. So now the second one would be glove option. So the glove option, basically you look at co-occurrences of the words that appears between in the corpus. So we consider, for example, what would be the probability of the given word. It could be random, it could be selected a list of the words by given eyes. So while processing a large number of the contexts, then we could able to recognize, for example, how much frequency eyes appear with solid. So then similarly, we could do the display process and process for the different words. And in this case, we could able to understand the semantic of composition of the, for example, ice and steam. As you can see, the highest level and the lower level, and then the other words would be canceled out. So the objective function of these, basically, we are looking to understand what would be the co-occurrences probability for target word, ice, and steam with a selected context word from a 6 billion token corpus. So the dot product equal to co-occurrence, and then we're going to limit this by using the cap f function, which means more frequent word would be cap and then be considered as a 1. So the text analysis through pre-trained language model, we're going to select the corpus and then we use the pre-trained language model, and then we could have some task like a sentiment analysis, similarity, and other results we could capture. One of the tools that we can use is Spicy. So for instance, we can do the text cleaning, analyzing, anonymization, tokenization, and semantic search. So let's try by do the first considering this content. I'm going to load those libraries. As you can see, we will going to, in this session, we will use the transformer and TensorFlow, as well as the other packages listed here. So then we're going to look at some sample EHR. So this sample EHR actually captured from the medical codified website. So it's some sample EHR record. So we can see the context, how it looks like. So now we're going to process this context and ask a couple different questions from this corpus. This is one single EHR record, and then we're going to load the spicy and load this text content. So basically, if you need this Jupyter notebook, to execute and reproduce result. In the first page, there was a QR code, so you can download the slide as well as you can download the code and execution of these lines. Anyway, so you can see we can look at the provide the text, and then text we can tokenize, which means we can separate each element, and by processing those elements, we can understand different segment of the text. So then now we're going to limitizer to use to understand the root of those contexts. So for instance, as you can see, we have a diagnosis, variety of diagnosis. We can reduce that word to diagnose. So then we can understand all those variety of diagnose in terms of the spell. We can have one single word in our data set. We can capture the content, like for example, we can look at what would be the pause, or for example, what would be the in term of in the context, selected context, what would be the actual, could be verb, it could be noun, or what would be the structure of the word in the sentence. We can also use the displacity to visualize this context, as you can see on the screen. So basically, we are going to look at the diagnosis with COVID. So then you can consider what would be the structure of this sentence. Now we're going to look at the, for example, different documents. Let's say if we have a list of different words, and then we can look at the similarity of between these words. For instance, what would be the heart disease, cardiovascular, diabetes, and device. As you can see, device is completely off from the other words. So let's see how using just only a pre-trained language model, how we can recognize that. So first we're going to look at the similarity. We generate the similarity array, and then we're going to produce the vector representation of each word. And once we generate the vector presentation of each word, then we're going to check the similarity between each words. So now let's say similarity produce a pair of for each one. For example, we have a heart disease. What would be the similarity? Heart disease to cardiovascular, heart disease to diabetes. And then we generate a set of numbers. Now let's visualize that to see how it looks like. So now we're going to visualize this context. So as you can see on this screen, now we're going to look at the visualization that shows, for instance, the heart disease has some similarity to the heart disease. Of course, would be 100%. But if you look at the other context, we could have other possibility of similarity. And as you can see, and we expect that the black colors shows low similarity to other words, which means the device does not match with other words that would be considered to processing the text. We can understand the text of the device is not relevant to heart disease, cardiovascular, diabetes. So basically, as you can see, diagonal shows the pair of itself and is always 100%. And now we're going to look at the word to vector model as we explained. Now we're going to load the models. So there is a couple pre-trained models already exist. One of them we could use is a GenSim, and then the GenSim actually I'm going to use, for example, one of them is Glove Wiki GigaWords, and then another option is we could use a specific word to vector for biomedical terminology that you can download this file from these links. So these links actually around 30 GB gigabyte file. You have to download that to execute. So basically we load this one. but we will limit this to top 1 million records. So which means we're going to look at those top frequent words that appear. So if we remove this limit, in my time gets requires some time to load the model. So, okay, so now we're going to load the model. Once we load the model, now we're going to, same thing, we look at the similarity. So in the similarity of this pre-trained language model, we're going to say, what would be the positive disease and cardiovascular, but we don't want to have a negative diabetes. So which means we have some disease relevant to health disease, but we don't want to have a diabetes. So as you can see, the pre-trained language model, it returns couple different answers. Actually, once we need to understand the context, we could possibly actually to reduce the noises by fine-tuning or generating a new trained model that would be produce this specific task for medical. So similarly, we could possibly say, what would be the most similar words, cardiovascular top 10 words in this pre-trained language model? So again, this is a large language model. As you can see, is learned from the PubMed, and it's possibly can return the list of, for example, diabetes. As you can see, it returns diabetes, 2 diabetes, type 1 diabetes. So pretty much the model, as we have more data, then we can understand more context. Similarly, we could understand, for example, the list of words in this list, which one is not matched. As you can see, it shows the device. Similarly, if the same word, but use the HCM rather than the device. So now we're going to say which word does not match with others. As you can see, HCM is type of the heart disease, so then diabetes would be different. Another one, we could also understand the distance between the cardiovascular diabetes, cardiovascular heart, and as well as we could also look at the context, which is basically generate the vector representation that for the cardiovascular is it. So as you can see, it's a top 100 we retrieve, and then we have the numerical representation for the vascular, and then we have the numerical representation for the heart. So this is basically the approach that we've been able to process the context. So the next one would be the transformer. So the transformer actually include the two part. One part is considering the encoding. So the idea of the neural network, there is a actually, for example, in the historically, you can see the LSTM was initially introduced, but it was time consuming to generate the model. But now we're going to use the transformer to that help to understand using the multi-head attention, basically encode the content, and then in the parallel, it can decode the content. It can go faster in neural network. So now we using, for example, attention layer, we can see the context. We can see, for example, what would be in the one layer on the left-hand side, you will be able to see what would be the context in the fourth layer after training. And then on the right-hand side, you can see the same input. What would be the visualization attention in the term of the terms in the layer 5? So similarly, the approach almost the same year published BERT. So the BERT model actually is going to consider what would be the context we have, and then mask the sentences, and then we can randomize those values, and we can generate a set of value that can be replaced for the specific mask. And based on that one, we could generate a pre-trained model that can capture everything. But in the fine-tuning step, we could possibly, for a specific task, like for example, question answering, that use the squad to understand what would be how to answer the question by using those structure. Similarly, we could apply the other features, like for example, NER to, for example, recognize each items. So basically, 50% of the word to predict, but don't replace with mask with 100% of the time. So that would be save the time. So basically, there is a BERT base that 12 layers that includes 768 hidden layers with 12 head, as well as there is a BERT large with 24 layers that include 1024 hidden layer and 16 head. So the basically, if we process the context, then we have at, and then we mask the context, and then we're going to understand what would be replacement of this mask, how we can replace this mask with another words, and more likely would be mask replaced with high risk in terms of this context. So in terms of the text classification, we could possibly corpus pre-train and then fine-tune the healthcare domain data set. And then as well as we have some input text, then we can fine-tune and language model and then generate the different classes. Another scenario is question answering. So the question answering is we could use the structured data, and in the structured data, as you can see, there is a table that we're going to answer the question based on those table. As well as there is a knowledge graph. We might need to, we might have already exist the knowledge graph, and then we want to answer the question based on the knowledge graph, or we might process the context and generate the knowledge graph and then answer the question based on the knowledge graph. Another one using the unstructured data, which mainly we are dealing, and in the demo, I'm going to show this part and considering the unstructured data. So one of the question answering type is open generative question answers. So for instance, given like a question like this, for example, we have this, what are previous diagnoses for the patients. So there is some description that in the EHR record we already capture. So now we're going to answer, but there is some signal that shows where is the answer, previous diagnosis with, and then there is a yellow boxes that shows what would be the answer. So then basically the open generative question answering, the model generate the free text directly based on the context. The second one is extractive question answering. So the extractive answer from the context here could be provided text, a table, or even HTML, or any kind of context we could have. This is usually solved with BERT-like models, and what is the disease of the patient, for example. And then we're going to answer based on the description, which is written in the EHR, for example, provider generate this context, and then we're going to answer that. What are prevention method for ASCVD? But in the EHR record, we were not able to capture this context. So this is another type of question answering that we call it closed generative question answering. And then you need additional resources such as Wikipedia, such as, for example, other resources or other data set that we already have, and we can use those resources. So now we're going to look at those contexts. So basically we look at, to give some example in the demo, we have a couple questions that we're going to ask from the corpus. Each one has a different text, for example, EHR record, and then we use the pre-trained language model. Again, we're not going in this demo, we're not going to look at the a specific fine-tuning process, or we're just using out of the box applications. All right, so now let's start by this question answering. First, we're going to use the transformer, and then once we use the transformer has a pipeline, and now I'm going to use a model, this Tilbert, which is much faster than other models. So we're going to load this model. is for question answering, already trained and fine-tuned. So now what are previous diagnoses? Again, this model is already pre-trained and exists on the internet, so you can easily load. So now, what are the previous diagnoses? So basically, if you recall, this is the text, which we're going to look at the context and answer based on this context. As you can see, there is an answer in this text we're going to answer. So now, as you can see, it returns the answer. Basically, shows the familiar and pure hypercholesterolemia. So then we a score of 36. So then it also shows where it's located. So we can see the answer where it's located in the context. We can also, what is the disease of the patient? So we can look at the context and we can process that. And as you can see, again, we can able to answer the question, again, by using the pre-trained language model. We're not doing the fine-tuning. So even if we do the fine-tuning on the a specific, for example, healthcare domain, we could possibly improve and remove some noises, as well as it could improve the confident level of the retrieve values or scores. So again, we're going to now use the sentence transformer. So the sentence transformer is using the pre-trained language model. We're going to load from the Allen AI Biomed Roberta based model that's publicly available. So now we're going to use the context, and then once we use the context, we're going to generate a text classification. So it's already pre-trained. So for this task, so now I'm going to have some context that shows the sentence that I have. I'm going to ask the question from this sentence. So basically, I'm asking, does the patient previously diagnosed with diabetes, by asking from this question. So if you ask, basically you can see it shows three different classes. One is a contradiction, as you can see. So because it's relevant to the heart disease, so it's not relevant to diabetes. So as you can see, it returns the contradiction. So by processing this context, you can see the different answer actually exists, but it's not actually semantically we need to understand. So that's the reason it returns the contradiction. So now then we're going to ask another question. Let's say patient diagnosed with heart. So what does it mean heart? So that's not clear, right? So now you can see its response neutral. And if we extend that one rather than heart, we say heart disease. So now you can see it's return entailment, and then it's basically you can see the score as well. That return the result shows the previous diagnosis with heart disease. So now let's another example. So review another example. Let's say we have the text, and then we're going to say what are treatments should be initiated in this text. So we can process this EHR sample record, and it returns the answers. So again, we are doing all those question answering without any specific fine tuning on the specific domains. It's general. So now we have the answer as well as for the score and as well as for the start and end location of the position of the answer inside the text, where we could possibly find that context. So basically, as you can see, we can have the different contexts, but once we capture the context, let's say, for example, we have a variety of the answer, but we want to consider the text that categorize into different categories. For example, let's say we have class of heart disease, cancer, diabetes. So how we can do that? So now let's focus on this part. We have the answer to. So if you recall, the question was, what is the disease of the patient? So then we got the answer, and now we have the answer. We have the if you recall, this is the text which we captured the answer. So now we're going to say we have three classes that include the disease, cancer, diabetes. So now I'm going to select these three different categories and then find the similarity between the heart disease and the answer which we capture from the question answering. And based on that answer, we can possibly respond to classify, say, the specific answer which we capture, where it come from, what is the source of that, and what is the class of that. So again, we're going to encode, which means generate the vector representation, numerical vector representation. Once we capture vector representation, then I'm going to use PyTorch cosine similarity between two different vector representation, which means, in another word, I can capture the similarity between the answer and the class. So once I capture this, all those similarity put in the array of the cosine scores. So then if you look at the embedding, basically each context we embed, we capture based on the BERT model, we use the embedding, and then if you look at it, we have the 768 vector number representation, and then we can look at the numbers. We can look at what does mean each word when we embedding. And then we can look at also the similarity capture for each element. So let's make it more visible. So now you can see heart disease has a 92, and cancer has a 91, and diabetes has a 92%. Now say use the argmax to find the maximum among those content. As you can see, the answer classified as a heart disease. So similarly, we can extend this context with other features. So that was actually the reason we could possibly, for instance, in unsupervised pre-training model, we could have the text, and then we could possibly recognize the different classes, or we can supervise fine-tune models for a specific context. As well as there is another approach that we can use the BERT by using the masked language models. So another one, we can look at the masked language model. We basically preload the context of from the Microsoft Biomed NLP, which is trained from the PubMed and large number of the paper around the medical area. And then this pre-trained model, so then I'm going to look at this masked language model. This is original context, and I'm going to mask one specific element. In conclusion, based on use case, different language model can be used, such as word-to-vector, graph, BERT, GPT. Pre-trained language model can be used easily and works well across different domains, and the latest pre-trained language model are expensive. Regularly, we try to use the DistillBERT, or even if you want to train the model, it might be slightly time-consuming, as well as would be expensive to train from scratch. The pre-trained model also can be fine-tuned on a specific domain downstream task. Thank you for your attention and joining this session. I would be happy to take any question if you have.